want to say a little more about annuity formulas. This is something we have looked at the basics of in class, but I want to take a little further. So here's the way I'm going to write things down. It's very standard compared to what I did in class, same letters. We're going to have an annual deposit, D dollars per year, and an annual interest rate of R. And of course, we're going to have to make sure that we're careful about percents versus decimals on that. And we're going to leave it in for T number of years. And then with anything about annual versus monthly, we're going to have annual numbers and the corresponding monthly numbers. Well, I'm going to call the monthly deposit A1 because it's exactly the A1 that comes into a geometric summation. I'm going to look at R, little r is the multiplier or the ratio, and that is crucially given by 1 plus R over 12. And then n, if we want to talk about that, that's the number of compoundings are going to happen, also the number of contributions we make to the account, and that's the number of months, and that's going to be 12 times however many years have gone by. Okay. Oh, and of course the monthly deposit is going to be, oh, I put these down and I forgot I put these down a little later as well, so it's going to be a little redundant. Okay, so if we didn't have a lump sum to start with, this is the simplest case of an annuity. This is what we figured out, that you can just calculate these three numbers, which I conveniently have again here, and put it into the summation formula for a geometric summation. Pretty nice, okay? Or if you want to put everything in, combine it, you put in your d over 12, you put in your 1 plus r over 12, you put in your 12t, a little bit of cancellation happens, and you get this somewhat more streamlined version of the formula in terms of your three crucial numbers: yearly amount of money you have to contribute, annual interest rate, and number of years t that have gone by. Okay, but then in class we got to a little bit of a different situation, which wasn't much of an extension of it, which was we start out having a lump sum in the account. Right at the start, it's got an initial principal P, not just 0. And then additionally, we regularly deposit money. Okay, so all we get, it's as if we had two accounts, and we could actually do it physically as two accounts in the bank. Here's our lump sum growing with standard compound interest formula. That's exactly what we've been doing before, plus the slightly more complicated formula for the annuity. Okay, and you can rewrite this. You can combine the 1 plus r over 12 to the 12t's if you want. It can be nice for algebra, but I'm just going to leave it that way to emphasize the separate nature of the lump sum contribution and the annuity contribution. Okay, so I want to do a quick example of that since we didn't, in some classes, we didn't have a lot of time to do that. Okay, so I put in $50,000 as my lump sum, and then thereafter I invest $3,600 a year. There's my D. And let's say it's 8% interest. That's extremely good for like a bank account right now, but it's not implausible if you actually think about this as like the stock market or something. And we're going to assume it's compounded monthly, so this formula is right on the money. Okay, how much money do I have after 40 years? That's just straightforward plug in into this formula. And that did not work. Somehow I did not like my control C there. Okay, so there's my my formula, and I'm going to plug in the 50,000, 0.08. Remember, you've got to convert that to a decimal, or else it's not going to be remotely correct. I'm putting it in for 40 years. Okay, and then the 50,000. Ooh, what did I just do? I'm not paying attention. This is the 3,600. Easy mistake to make. So I'm almost glad I did that. So really important. This is the initial principal. That is just rocking along as a lump sum put in and you don't touch it. This is the yearly deposit. Really crucial. That's the big D. So don't get those confused like I just did. Okay, and then here's another 12 times 40. Okay, so let's actually just evaluate those. And I want to evaluate them separately because I'm curious about how much contribution, how much of the money I get at the end is due to just my initial lump sum, and how much is due to my progressive savings. So this is going to be, ooh, a little over $1 million, 1.0, well, let's just write it out. It's not even actually giving me a whole lot of precision there, but it's just fine. Okay, so there's $1 million coming from the annuity part. And here is something that I think is probably pretty comparable. In fact, it's more. So that's 1, 2, 1, 3, $700. Okay. And then the total, of course, is just going to be the sum of those. Ooh, it's probably not going to like my dollar signs if I wanted to. It's probably not going to want my commas in there either. Let me just erase the commas for a second so I can get it to do it on the computer. So about $2.2 million. Yep. So $2,261,000 to the nearest $1,000 because it was rounding for me. Okay. And I'll just put it in here. Okay, so that's so far so good. Hopefully that's a straightforward use of this formula. And we're seeing that that 50,000, that was a pretty darn good initial investment, and it's actually a bit more than 50% of the final amount. That said, I'd be missing out on $1 million at the end if I hadn't put in this 3,600 a year or 300 a month. That's pretty good amount of money to put in as well. Okay, so in the next video, what I'll show you is I'll go back to the spreadsheet where we discovered this, and we'll see how to do a debt with this. Oh, let me actually show you one more thing though. I forgot about this. What about if I'm not looking for a fixed time interval and how much money I get. I'm looking for a fixed desired amount of money and how long is it going to take to get to there. Okay. Not something that's impossible to do algebraically. It's not really that bad. If you just plug in 400,000 for the amount and put a t back in the variable, that's really doable. But I want to show you how to do it on the TI calculator. So I have that set up here. So I plugged in with, it's a little laborious to plug in this whole formula carefully, all the parentheses really careful. 3600 over 0.08, 1.08 over, wait for it, 12 to the 12x, etc. So I'm just putting in an x as usual where the time variable would be, putting in both parts. You could make this a little more efficient, but I'm still keeping them separate. Okay. And then I'm putting in as a y2, I'm putting in $400,000. Okay. Now, I already know what a good window would be for this, except that it's just getting really confused, and it's refusing to show me the window. That's not helpful. Not sure what I can do about that. It's being really strange. Okay, there we go. So I'm going to go 40 years, since I know it doesn't have to take me 40 years to get up to $400,000. I got up to 2.2 million in that time. And I'm going to go from 0 to say 2 million, since I know that's about the right amount for Y. Okay, now I'll go to the graph. Ta-da! So here's my growing amount of money. It looks really close to an exponential. Remember, it's not quite exponential. If we did it on a semi-log graph, we'll do this a little bit, we would see it's not quite a straight line. And then here's 400,000, and here's my time. So if you go to second calc, intersect, number 5 here, yeah, first curve is that one, second curve is that one. I'm already near the guess, and it's going to tell me about 19.4 years. Okay, so about 19.4, a little under 20 years out, I'm going to hit that mark of $400,000. So that's another thing we could do. So in the next one, I will show you how to deal with a debt. It's wonderfully simple.